Okay, yay. Our last note of the first unit. This is, as you can see, it's a mouthful. This is the force of gravity, and oh, it's a good one. And there's two ways of calculating gravity, and excuse me. We'll talk a bit about. We can see an equation here, but just like Sir Isaac Newton, he came up with Newton's laws, but he also he was the first one to come up with an equation to model gravity, and the first one to realize that gravity isn't just, things falling to the ground. Gravity exists between all objects. It's just that Earth, in our experience, is so massive compared to like anything we touch or see. Like the force of gravity between us and Earth is just ginormous then compared to, us and an apple or anything else. So we don't notice gravity because it's sort of between us and anything else besides the Earth. Now, interestingly enough about gravity, scientists sort of in the last 100 years have realized that the force of gravity is actually insignificant compared to the forces like electromagnetism and other forces within the atom. It's actually the weakest and really the least understood of all the forces, even though I think for us as regular people, just in our day-to-day life, we feel gravity all the time. So we think of it as huge and important, and when you wipe out, you realize it really is important because gravity hurts. But from a physicist's point of view, gravity is actually almost like relatively insignificant, which is, unless you're studying black holes or whatever. But anyways, that's big digression, because what I wanted to say here is that Newton realized then that gravity wasn't just between apples and the ground or us and the ground. It's between any two objects, and it is the force. He's the first one to realize that it is the force that makes us orbit the sun and make the moon orbit us. Right? It's all because of gravity. And he was the first to do that, and to realize that, and he was able to model it mathematically, give it an equation. And this equation, which actually was proven to be somewhat incorrect by Albert Einstein, is still close enough to accurate that we sent the all that was needed to get astronauts to the moon was a really good understanding of this equation right here. Okay, so even though, and he found this in the 1600s, which is pretty neat. He didn't, by the way, come up with this number, but he came up with this relationship. And so what all this stuff is in this equation, okay, Fg stands for force of gravity. Okay, this big G is a constant, and he couldn't calculate this constant back in those days. That got calculated later, but he knew the relationship and that there was a constant. And as you look at it, I don't know how well you're good with the scientific notation, it's a tiny, tiny number. Okay, and M1 and M2 are any two objects, the mass of them. And so this is measuring the force of gravity between any two objects, mass 1 and mass 2. It's like usually when we do it, mass 1 is the Earth, right? And then R stands for, in this case, R is the center-to-center distance between those two objects in meters. And you might ask, why R? Why isn't it called D squared? And the reason it's R is because when Newton did all his work, he really was looking at planets. And so, for example, if you're looking at the center-to-center distance between you and the Earth, it would be the R, the radius of the Earth. Plus the little bit of distance you are above the surface of the Earth, but pretty much it's the radius of the Earth, and that's why it's R. Okay? Things that are important when you're using this equation is that masses are kilograms, and that R has to be in meters. Okay, so let's use that equation. You can see that happening here. So Ferd and Ferdette are out in outer space, and this is the only time that we would experience gravity in this way. If you're not near anything like the Earth. So say they're in space and they're located a meter apart. Determine the force of gravity between them. And so using this equation then, and I really, really suggest you try it in your calculator, because putting this in your calculator is not an easy thing. Maybe I'll quickly try to do this on the Google Calc here. One sec. 70 and 60. So I'll just go Google Calculator and I'll show you how I would do this. So 6.67. Usually this is the button you can hit to get the times 10 to. Times 10 to the negative 11 times 70 times 60 divided by 1 squared, which is just 1. So this part's kind of irrelevant, but that would be how I'd type that in. So any different numbers, and that's going to be some tiny little number times 10 to the negative 7. Okay? So 2.8 times 10 to the negative 7. Gravity between objects in which one of the objects is not the Earth or a planet is always tiny. Okay? All right. So if you're not caught up, just pause it. Okay, another example. Ferd, who's 70 kilograms, is standing on the surface of Earth. Determine the force of attraction between Ferd and the Earth, and what direction is the force acting on Ferd. And I'll give you the answer to this part first. The direction is directly towards the center of the Earth. Now, interestingly enough, Sir Isaac Newton's formula also tells us, by the way, that the Earth is, whatever force Ferd feels, the Earth is feeling that same force towards Ferd. So the force is a force of attraction, which means that Ferd feels the force towards the Earth feels it towards Ferd. It's just that the Earth is really, really heavy. So while that same force can make Ferd, move really, really quickly, if you think about Newton's second law, more mass equals less acceleration. So, or in this case, less mass, Ferd's less mass would mean more acceleration. But the Earth has such a massive mass, there'd be almost basically a zero acceleration. So really, that's an interesting thing to keep in mind, Newton's third law. Okay, anyway, so ME, by the way, these two pieces of information, if I gave you a question on a test, I would tell you that stuff. That's the mass of the Earth and the radius of the Earth, so you don't need to know those things. Yeah, so those are the givens. You need to know the two masses and the R, right? And R in this case is distance from Ferd to the center of the Earth. So you can see that calculating gravity is a bit of a pain in the butt. Especially, now this one's even better, because you have to make sure that's squared, and when you put that in your calculator, you don't mess that up. And again, I suggest you practice it. I suggest you pause the tape, type that in your calculator, and see if you can get 686 newtons. You'll be very happy to know, by the way, that there is an easier way than this way. But let's keep going. Ferd is holding a 1 kilogram can of coffee while standing at sea level on Earth. What is the force of gravity between that 1 kilogram can and the Earth? So this time, we're not talking about Ferd, we're talking about his can of coffee, so 1 kilogram. And what I'm saying here, when I do this calculation, is how much force does 1 kilogram experience downward towards the center of the Earth? And the answer, and this number should interest you a little bit, is 9.8 newtons. 1 kilogram of mass at sea level feels a force of 9.8 newtons, which sounds a lot like our acceleration due to gravity. And in fact, they're the same thing. So you could reword this to say the force of gravity at sea level is 9.8 newtons for every kilogram, per kilogram. And that makes this 9.8, just like it is our acceleration due to gravity, it's also something special called a gravitational field constant. So if ever you're wondering, we've been sort of doing some calculations with forces, and it's like, well, what's a good number? How do I know? Now, if you put a kilogram object in your hand right now, you could go to the back of the room and grab one of my masses, put a kilogram in your hand, and that force downward that you feel, that's 9.8 newtons, or 10 newtons. And that's what 10 newtons feels like. And actually, the force your body's feeling towards the center of the, say you're 100 pounds, or 100 kilograms. We can't talk in pounds. Say you're 100 kilograms, which I don't, you have to change your mass into kilograms. That's about 1,000 newtons that you feel downwards. Okay, so this 9.8 is a special thing, and it has a special symbol, little g. Doesn't that familiar? The gravitational field constant, which is also the acceleration due to gravity, at the surface of Earth is 9.8. That number is great for the surface of Earth. It's different everywhere else in the universe. So since we know that every kilogram mass on the surface of Earth feels this force, though, it does make it easier to calculate gravity. Okay? The force of gravity between any single object and the Earth, which is usually all we calculate, all we care about. Not many of us are doing planetary science here. The force of gravity is any mass in kilograms times 9.8. Period. So you want to find gravity? This is the equation we almost always use, because it's 9.8 newtons for every kilogram of mass. So finding the force of gravity between 70 kilogram Ferd on Earth is 70, his mass, 9.8. You multiply them, you get the same answer. Okay? So just a few more examples. Find the force of gravity acting on these objects with Earth. So 10 kilograms, you just multiply 10 times 9.8, 98 newtons. 200 grams, careful here. The 200 grams, you have to change it into kilograms. I know I'm going fast, but I hope you pause it if you need to. Okay, so the 200 grams, you divide it by 1,000 to get kilograms, and you multiply that by 9.8. So 200 grams feels about 2 newtons. And 500 kilograms, exact same calculation, 500 times 9.8. Okay, so that's calculating force of gravity on Earth, which almost is always what we do. We don't calculate many other places. But that doesn't mean we can't. Finding the force of gravity on other planets. So the 9.8, if we use the same train of thought that we use to find the force of gravity on Earth, which is just basically saying find the force of gravity between any 1 kilogram object resting on the surface of a different planet, we can then find the moon's gravitational field constant, or Jupiter's, or anyone else's, okay? And so for the moon, you just need to know the mass of the moon and the radius of the moon, and that's only a Google search away. So the mass of the moon, 7.35 times 10 to the 22, and the radius of the moon. So right, we have to go back to this equation because we're not talking about the surface of Earth anymore. But you could do it, and what you find is that the gravitational field constant on the moon is 1.6 newtons per kilogram, which makes sense. It's a lot less than Earth's. We're 9.8. Well, the moon is a lot smaller and a lot less heavy. Like, the small isn't actually the big deal. It's the fact that it's less dense. Because if it was the same, say it was the same, like the size, say the same size as this, which is a lot smaller than Earth, but if it had the mass of the Earth, then it would be even, then this number would be even greater, right? Because it'd be more dense. More dense would be more gravity. Jupiter, same thing. We're going to talk about 1 kilogram mass. We're going to find the mass of Jupiter and the radius of Jupiter, just a Google search away. And what you find is that the field constant on Jupiter is 25.9 newtons per kilogram. Okay, so you could find the field constant anywhere on any planet, and you can, of course, that'll be part of your assignment because that's awesome. And because you're supposed, but you're not allowed to Google it. You could probably Google gravitational field constant on Saturn or whatever, but you got to show me the calculation because it's awesome. You don't need Google anymore. Maybe just to find those information, but. Okay, just one last thing I want to say about force of gravity, and this is a terminology thing. Weight in the physics classroom, weight is a force. Weight is the force of gravity specifically. Weight is not mass. So we do not use, you don't say to the person beside you, what's your weight? Well, you could, but then the answer your friend better give you is 800 newtons or something like that. If they're asking you your weight, it's asking the force of gravity. It's not asking you your mass. And please be aware of that. Language-wise, if you write down weight, right, that's not good communication. It says maybe you don't understand the difference. So weight is gravity. Weight is measured in newtons. Mass is measured in kilograms or pounds. Okay, and I think that's all I have to say about gravity. And that's the last note of the unit. So, ta-da!